There's a river in southern Tennessee that runs out of water without a drought. It comes down off the plateau, crosses a valley floor, and then, at one particular spot, it just goes into the ground. Downstream from there, the riverbed is dry. Not low, dry. Bare cobbles and leaves for miles most of the year. Then, several miles further on, water comes back out of a hillside, and the river picks up again. Nothing was lost along the way. It just spent that distance somewhere we can't see. And here's the part that turns this from a curiosity into a pattern. The river doesn't sink just anywhere. Geologists who mapped that valley found the water goes down almost exactly where one rock layer meets another. Draw the boundary between those two layers on a map, and you've drawn the place where the river ends. That's not a quirk of one valley. It's the visible edge of something a lot bigger. I'm Grant Calder, and this is Beneath America, where we look at the ground under familiar places and what it's actually doing down there. Today, the rock under a long stretch of Appalachia and why parts of it keep opening up. If that's your kind of question, subscribing helps. The United States Geological Survey has published a map of potentially karstic carbonate rock across the Appalachian states. That's a mouthful, so let me unpack it. Carbonate rock is limestone and dolostone, the kind of rock that groundwater can slowly dissolve. Karst is the landscape you end up with when it does. People sometimes call this a sinkhole belt. It's a useful phrase, and I'll use it too, but it isn't an official name, and it isn't one continuous thing. The map makers called their own version preliminary, and they called the rock potentially karstic. Those hedges are doing real work. What that map actually shows is carbonate rock reaching the surface in long strips and scattered patches across more than one geological province. Look at it with the state lines turned off, and the shape gets a lot clearer. The pattern runs from Alabama up through Georgia and Tennessee, along Virginia and West Virginia, into Maryland and Pennsylvania. It doesn't stop at borders because rock doesn't. Nationally, about 18% of the country sits on soluble rock of one kind or another, and every single state has a little of it. So why is the soluble rock lying in strips through the middle of a mountain range? Go back about 500 million years. This part of North America sat near the equator, under a warm, shallow sea. Shells and skeletons and lime mud settled on the bottom, year after year, until the pile was thicker than you'd want to imagine. In the southern Appalachians, researchers have measured that ancient carbonate at up to about 2 miles thick. Then the continents collided and built these mountains. Those flat seafloor layers got folded and faulted and shoved sideways until they stood at an angle. Erosion has been working on them ever since, and erosion is picky. Hard sandstone resisted, and it holds up the ridges. Carbonate gave way faster, and it became the valleys. Which leads somewhere most people don't expect. The flat ground, the good farmland, the easy routes through the mountains, the places where towns went in, and where Interstate 81 runs today, those are largely the carbonate valleys. The reason that land was worth settling is the same reason it dissolves. The main carbonate aquifer down there is thousands of feet of Cambrian and Ordovician rock, and it supplies towns along that highway corridor from Tennessee all the way up to Pennsylvania. Now, the water. Rain falls, picks up carbon dioxide from the air and from the soil, and turns into a very weak acid. Weak is the important word here. It's a lot milder than vinegar. You could stand in it all day and never notice. But it has time. That faintly acidic water works its way into joints and cracks and the seams between rock layers, and it takes a little carbonate with it every time. A crack becomes a channel. A channel becomes a conduit. Give it enough of those years, and a conduit becomes a cave. This region holds some of the longest and deepest caves known anywhere in the United States. Most of it isn't cathedral-sized, though. Under a lot of these valleys, what you've got is a network of openings, some of them narrow, some wide enough to walk through, threaded through the rock below the valley floor. Not hollow ground, rock with a plumbing system in it. And people live on top of that plumbing. Which brings us to the word everybody knows, sinkhole. And most of what people picture when they hear it is the rarest version. Here's the thing I'd most want somebody to take away from this video. Most sinkholes aren't sudden, and most aren't dramatic. Geologists sort them into three kinds, and only one of them is the kind you've seen on the news. The first kind forms where the rock is bare or nearly bare. Water dissolves it directly, and a shallow bowl develops over a very long stretch of time. You'll find these in pastures and woods all over the region, and most people walk right past them. The second kind happens where sandy soil sits on top of the rock. Grains trickle down into the openings below, a little at a time, and the surface settles as they go. It's slow, it's often small, and it can go on for years without anybody marking it. A dip in a yard, a spot in a field that always holds water after a rain. The third kind is different, and the difference is the soil. Where the cover is heavy and clay, it holds together. Soil still falls into the openings below, but the surface doesn't follow it down. The material bridges the gap and forms an arch, and that arch holds while the empty space underneath climbs slowly upward through the soil. From above, nothing looks like it's happening. The grass is fine. The driveway is fine. Then the arch runs out of material to hold itself up, and the ground opens over a matter of hours. So the collapse isn't the process. The collapse is the end of a process that's been running quietly, sometimes for years, in the dirt rather than in the rock. That's why the soil above the limestone matters just as much as the limestone does. If that sequence is already underway, what decides the day it finishes? Groundwater does more than sit under our feet. It presses up against the underside of that soil and helps hold it in place. Lower the water, and you take away some of the support. That's a big part of why timing matters so much here. Drought lowers it. Then heavy rain does two things at once. It soaks the soil and makes it heavier, and it pushes water down through it, washing loose material into the openings below. Dry, then very wet, is a harder combination on this ground than either one on its own. Virginia's geologists recorded a clear example of that. In April of 2000, after 7 inches of rain fell on the upper Shenandoah Valley following a long dry spell, 32 sinkholes were reported. People can change the same variables. Pumping groundwater lowers the water level. A leaking water line or sewer pipe puts a steady stream where the ground never had one. Redirecting stormwater concentrates flow at a single point. Excavation, fill, and heavy loads at the surface all change what the soil below is being asked to carry. It's worth being careful about that because it's where a lot of coverage goes wrong. Those things are triggers. They aren't the cause. The cause is old rock with openings in it and soil sitting over the top. Human activity mostly changes the schedule in ground that was already susceptible. And there's a second half to this that gets a lot less attention, even though it may matter more. Whatever goes into one of those openings has to come out somewhere. Figuring out where is harder than it sounds, because underground water doesn't follow the valley you can see. So researchers use dye. Non-toxic fluorescent dye goes into a sinking stream, and detectors sit in springs and caves for miles around, waiting to see which one lights up. The results are often not what you'd guess from the surface. In one Tennessee study, a trace stayed underground for nearly 8 miles before it came back out. Another one reached its spring in under 30 minutes. That's roughly 1,400 feet an hour underground. And back in 2017, researchers expected dye to surface at a spring about half a mile away. It came out nearly 2 miles in the other direction. You cannot read the underground route off the landscape. Now here's the part that ties it all together. In 1990, a sinkhole opened in the town of Jasper, Tennessee after some construction work. Dye was put into that hole. 8 days later, it was detected at Blue Spring on the other side of town. Blue Spring is where Jasper gets its drinking water. There's a treatment plant sitting right beside it. The hole in the ground and the tap in the kitchen were the same system. That's the honest reason karst water gets so much attention from state agencies and from the survey. It's a genuinely good water supply. It's also fast, and it filters very little on the way. What that argues for is mapping and protection, and that work is going on right now. It does not mean well water across Appalachia is unsafe, and I don't want to leave you with that impression. So where does all that leave a map? Pennsylvania has been cataloging karst features since 1985. A compilation covering just 14 of its counties came to more than 111,000 mapped karst data points. And the survey that keeps that data describes its own inventory as incomplete. I find that reassuring rather than alarming, and here's why. The mapping has improved enormously. Laser scanning from aircraft, called LiDAR, can see through a forest canopy in a way that aerial photos never could, and it picks up depressions that were invisible under the trees. Geologists in Virginia and elsewhere now use it to flag candidate depressions across whole counties. But a person still has to check what the computer found, and often somebody still has to walk out there, because the computer finds every dip in the ground, and not every dip is a sinkhole. And here's what all that mapping actually produces. It shows where the rock and the terrain make these features more likely. That's susceptibility. It isn't a schedule, and it isn't a verdict on any particular property. The agencies are unusually direct about the limits. There's no national record of sinkhole collapses in this country. A state survey says plainly that occurrence is unpredictable and that a reliable way to predict one early still hasn't been found. The size of a collapse can't be judged from the opening at the surface, and that same survey is just as plain in the other direction, that sinkholes rarely happen. Which is about where I'd want you to land. We've gotten much better at seeing where the ground could give way, and no better at knowing when. Those are two different problems. People have farmed this ground, built on it, and drunk from it for centuries, and the useful response isn't worry. It's knowing what's underneath you. Beneath America goes looking for the geology most maps leave out, so subscribe if you'd like to see what's under the next state. And tell me which one. Because carbonate is only one kind of ground that fails. In other parts of these same mountains, the openings underneath aren't natural at all. Somebody dug them and then walked away.